Hey, so I've been working in AI, machine learning, natural language understanding for many, many years. And the focus of my career has really always been about creating products that real people can use to accomplish things that give them value. Now, look, unless you live under a rock, I'm sure you've heard about and noticed and are living in that you're living in this revolution around AI and machine learning and large language models. Sort of all of a sudden, computers seem to be able to understand human language. And not just understand it, but actually make it, like generate it, write things, use language and turn it into music, use language and turn it into pictures and videos. And so, I feel like we've talked about AI for like many, many years, right? But suddenly, like, computers seem to actually be able to exhibit human-like intelligence. Now, I have to admit that, for me as a longtime practitioner and person like tried to build stuff out of AI, I'm actually pretty shocked. Like this has kind of taken me by surprise. When I finished my PhD back, 700 years ago at the University of Michigan and came out, we would kind of half joke to each other, but half serious. Like, hey, on your resume, you better take off the words AI, machine learning, anything like that. Because people didn't want to hire that. Right? It was seen as kind of pseudoscience. That's not real computer science. That's a bunch of smoke and mirrors. That's alchemy. It doesn't really work. And even when you would build a system out of AI, which I did end up doing in my career, but man, it would take years to get a system to kind of work at a decent level to do what today we would consider a very simple kind of AI-based task. So suddenly AI seems to work. And like other major technological shifts, if you think about how the automobile changed the world or the internet or the mobile phone, I think from my point of view, I think it's really pretty likely that just like all of those things really changed pretty quickly the way that people live and work day to day, I think this new generative AI is likely to do that too. And so what I want to do in this talk is, first of all, I'd like to just talk at a high level about how do these large language models actually work. Not so much the math or the deep details, but I want to hopefully give you some intuition about what makes language hard and how do these models deal with it. And then second of all, I want to talk about some of the challenges that come when you try to actually use these amazing models, but to build real products. We all probably heard that, hey, these models, they lie. They make stuff up. They don't follow your instructions. They're not good at higher order reasoning. And so I'll talk about all of those and kind of how people are dealing with. And then I said, I'm a product builder, really, at the end. And so I want to show you at the end one example of a cool, I think cool, LLM application that my team in Google Labs is building. So look, if there's one phrase that I kind of want you to take away as we walk through this, it's this. Teaching is the new programming. Now, what do I mean by that? What I mean is that AI is becoming powerful enough that it's starting to become possible to actually create new capabilities, teach the AI to do new things without being a computer programmer. Now, some of your computer programmers, you know what that is. That's meticulously going through and giving the computer every little step and every condition and every little move to make about every possible kind of input. And so it's limited to a very small number of people that can do that. But I think it should be good news for a room with a lot of professional educators in it that teaching is going to become over time a more powerful way to enable computers to do new things. All right, so let's jump in. Okay, so how do these large language models actually work? Well, just like this complicated picture, of course, there's lots of little nodes of computation, and they're connected together, and there's zillions of them, and it's very complicated, and there's all kinds of math. I see E equals MC squared is even in that. I don't think it really is. So lots and lots of complicated math. I'm not going to talk about any of that stuff, but I will tell you, I hung out today with the Rice Computer Science Department, and I promise that any professor there will be more than happy to answer all your math questions in great detail. But I want to start from a different place, which is, what is it that makes language so hard anyway? I mean, for computers. I mean, look, like any 2-year-old, your son or daughter or niece or nephew, like they can do this. And once they start, you can't get them to stop. Like we all can do it, right? We all can talk. It doesn't seem to be like hard for us. We're not like working up a sweat doing that. And computers are so good at so many things. So why can't they do this? I mean, after all, I can take a series of numbers like this, and the series could be, thousands of numbers long, and it could have more complicated things in it, like square roots and divides, and I don't know. And then the computer can instantly do that, right? It can do it way better than we could do it. And so, like, doesn't language just work like that? Like it should be, right? Like there's some words, and if I know the meaning of each word, words are coming one at a time, just like they're coming at you right now, and I just add up the meaning of the words, and I should understand and get the meaning, right? Well, of course, we all know language doesn't really work like that, right? The problem is language is a little more complicated than numbers in a lot of ways. First of all, obviously, language can be ambiguous, right? So words can mean more than one thing. But worse than that, what the word means really can depend on other stuff in the conversation, right? What the word means can depend on what came before. It can even sometimes depend on what came after. Even worse, it can sometimes depend on the number we talked about yesterday. Like it can depend on something that's not even in the conversation, can dramatically affect what language means. And if you're gonna put it all together, and if you think about it a little bit, even words that in the dictionary might only have one meaning actually have a lot of subtle shades of difference of what they really mean, depending on all the conversation that happened around them, depending who's saying it, what you know about that person, even maybe how they say it. And so language in the end just doesn't really add up, right? Word meanings, both individually and what words mean together, they depend on the context, right? All the other words and even things not there. This little picture is here to remind me to say a little story, which is just to demonstrate. So one day, a few years ago, I walked into the office. I hadn't said anything to anyone. I saw my buddy across the way. I walked over to him and I said, "Oh my gosh, that was ridiculous. That was just unbelievable." And he's like, "That was off the hook. It was mind-blowing." And then we walked off. That was our conversation. And we both knew exactly what we meant, because it turned out that the Giants were in the World Series and had a ninth inning, ridiculous finish to the game that went down to the last pitch the night before. That wasn't in our conversation. And if you think about those words I said, there could mean many, many different things, right? But in that case, that's what they meant. All right, so great. So words can mean all these different things. So how do we deal with that? All right, well, here's a theory of how to do it. Let's use rules to construct kind of what the meaning means. So what we'll do is we'll write down the possible meanings for all the words, and then we'll write or learn or induce a bunch of rules. And the rules will be about, given how the words are positioned with each other, maybe their syntax, you're in a prepositional phrase relative to that thing, and all kinds of subtleties. We'll write down all these rules, and then when we get some new words, we will run this rule system in order to compute what the meaning is. And it sounds pretty good, right? I would say, the field of natural language understanding tried this for, 50 years or something, 60, I don't know. People tried this for a really long time. You get very tired doing this because it turns out that there's many, many rules and many subtleties. But really, practically what ends up happening is you can really only succeed at this for very narrow systems or very narrow domains of language. You can succeed and make it work, but it's just too hard to do it for language in general. There's just too many subtleties there. So here's another solution. And the intuition of this solution is the following, that, if we're in a conversation, I demonstrate that I understand what we're talking about by knowing what to say next. If you think of my friend and I talking about the game, if after he said that was off the hook, it blew my mind. If I said, "Yeah, I hope I don't drop another bowl of spaghetti tomorrow," he would have been like, what are you talking about? Clearly you didn't understand our conversation. Whereas if I had said, "Man, I can't wait until tonight's game," then I would have been showing that I actually understand, right? So and we all do this with each other, right? We kind of gauge how much we understand by knowing what to say next. So if we could just predict what comes next, well, maybe there's a way to do that by having the computer read a lot of text and a lot of conversations and kind of learn somehow to predict what comes next. Then we would have a system that understands. All right, so this thing that takes a bunch of words that are coming in and predicts what words come next is what's called a language model. So if you hear the phrase large language model, you say, well, what's a like the definition of a language model is kind of literally that. It's a thing that predicts what words come next. Now, how can we build one of those things? Well, early on, people said, well, you know, now computers weren't very big then, and there wasn't that much memory and all those things. So they said, well, maybe given some of the words that came before, but maybe not too many, because I don't have too much space in my computer, we can kind of come up with probabilities that say, given the words that came before, what comes next. So this is called an n-gram language model. So given n-1 words, predict word n. So like a trigram means 3 words would be like, given 2 words, predict the next word. Okay? So how do you make one of those? Well, here's a way to make one. You can take a big pile of data, say you take like all the pages of Wikipedia or something, and you run a 3-word window across all the words. So you gather each 3-word thing that appears, and then you look at every 2-word prefix and basically make a table of the next word, right? So if you say, well, all the times that to the appeared in Wikipedia, what comes after? Oh, well, the word next was 34 times, to the next. The word first was 22 times. They weren't really, I made up the numbers. But, and then you can turn that into kind of a probability thing. And then when you want to predict, you can say, well, okay, given 2 words, we'll just look it up in that table and see what word comes next. So to the, well, next is the most probable word next. The next place, that. And this way, okay, you now have a language predictor, right? And you're forming a sentence. To the next place that I went. Okay, so that sounds pretty good. That can predict. No, I was too lazy to try to like write a Wikipedia trigram thing to show you, but I thought maybe we could just do it together. So I'd like these folks here in the front row, thank you, are gonna, if you're willing, can you please be my trigram language predictor? So here's how it'll work. I'll give you 2 words, and once I give you the 2 words, I'll point at you. Start with you, if that's okay. And you just call out what you predict the next word in kind of a sentence would be. Okay, ready? Okay, Bob went to the, or Bob went to, you already said the. Okay, so now we have to the backyard. Great. Sorry, they finished their sentence before I got to you. All right, so Bob went to the backyard. That's great, right? That's a pretty good sentence, right? I mean, so there you go. It works pretty well. Well, it is a good sentence. I like it. Maybe it's a good sentence, but it turns out 2 words just aren't enough, and even 5 words, even 10 words. It's just not enough to really know what to predict. Because, see, the thing I didn't tell you about Bob is Bob was very unhappy. That's what came before. So, see, now Bob might have gone to the backyard. Maybe that's like his happy place. Bob might have gone to the therapist. Bob might have, gone to his room and shut the door. I don't know what Bob did. It turns out what I didn't tell you is actually what came before is Bob had just watched the Astros lose the championship series. Is it too soon? Sorry. To the Rangers, Bob, of course, is a huge Astro. I mean, who isn't, right? And so Bob was very unhappy. So now where did Bob go? Well, maybe not to the therapist now. Maybe Bob went to the bar to have a beer, right? To drown his sorrows. But actually, what I didn't tell you yet about Bob that kind of came a few pages earlier in Bob's story is Bob swam over to Samantha. See, Bob is actually a fish. This is the thing that you didn't know. Now, what's interesting about this, if you think about it, now that came 10 pages earlier of text, right? But obviously, the fact that Bob is a fish is going to affect where you think Bob went, right? Of course it should, right? And so we can keep going with this, right? And so the point being, of course, like language that comes earlier can deeply, even one word like the word guppy there, can deeply affect what you should predict much later. And that's what makes language really hard. So what do we need? We need a capability that is some kind of structure that's able to capture those long-range relationships between words and how words, even that are far away from each other, affect each other's meaning, and thus affect the meaning of the whole context, and thus affect what you should predict next, right? And that structure is called attention. So attention is a mathematical construct, I guess I'll call it that. But what attention enables is for any word, whether the word's 5 words earlier or 5,000 words earlier, to have an impact on the meaning of the other words individually and together. And the reason it's called attention is because people like to say, well, the mechanism allows a word to know what other words in the context to pay attention to that are going to affect its meaning. You know, a lot of times people show this with pronouns, right? Like, you know, if the word is it, well, it's going to pay attention to a kind of an inanimate object probably versus, you know, a he or she or some other word, right? And so the understanding of the whole context through this mechanism is really improved, and it improves what comes next, predicting what comes next. So how do you train this thing? Well, we all have heard that, you know, these models are trained on massive amounts of text. I kind of think it was like the whole internet or everything ever written or something. And so by allowing these systems to see huge amounts of text and try to make predictions, they end up learning how the different words in the context affect each other. And because of that massive amount of training, you can think of it as like these systems, if it's Bob Went, they've seen like every time, or like any context possible for Bob Went. And allows them to form very accurate predictions of what comes next. And then at prediction time, basically we're computing attention across that context, and attention ends up finding the most likely set of words that comes next. I don't know why they're not appearing. Oh, there they are. And so that's attention. Now, obviously, we could spend a lot of time on attention in all its complexity. I'll just give you kind of your cocktail party fact in case, I mean, some of you already knew this one, but you know, which is the famous paper that kind of started this whole generative AI revolution was called Attention is All You Need. And the reason they called it that is because people, of course, had recognized this long-range dependency problem for a long time and had tried many different ways to kind of get that thing to work and taken that into account, and attention turned out to be kind of the mechanism that solved that and is the basis for these models. Okay, so if a language model is a thing that predicts words, and attention is this mechanism that lets it do it well, what about the large part? Like, we call these large language models. And you might have noticed, like, they're getting larger, right? So a few years ago, you know, think of the number there, the 340 million. Think of it as like the number of those arcs, kind of. That might be a way to think of it. You know, and obviously they started with hundreds of millions of those kinds of attention things. And now GPT-4 is rumored to be over 1 trillion. Of these things. So one question might be, well, why are these things getting larger? Like, why do they have to be so big? Well, there's actually a couple of reasons why that I think are maybe pretty clear from what we've talked about. One is, we just saw how, you know, you can predict a lot better with 100 words than 2 words. You can predict better with 1,000 words. People now are making these models wider and wider and wider. And so there's models now that can take 30,000 words. It can be Bob's whole life story in the thing before you have to predict where he went, right? You can know all about Bob beforehand, and that makes your prediction better, right? So that's one reason the models are getting bigger, is they're getting wider, if you like. Another reason they're getting better is that people have found that if one, let's call it layer of attention, different ways that words attend to each other, is good, actually you can capture even more subtle differences of meaning by having multiple layers of attention, essentially letting the system learn in more than one way how words affect each other. And so they're kind of making these systems taller and taller too. And if you kind of, you know, just multiply the width times the height, this will tell you, you know, why NVIDIA's stock is doing so well. Because these things take a massive amount of computation to use. All right. So we got these very large models. They're able to predict what comes next. So what? What do we care? Why is that interesting? Well, the reason is it turns out that predicting what's next is a very, very general problem. And of course, all of you who've used ChatGPT or Bard, you know this, right? Like, things actually do a lot of different things. You know, if I just say Bob went to the, you know, hey, this is a super simple Mad Lib problem or something. But if I say John had 6 apples and the rest of this, now I have like a math problem solver. Now the thing is still just a word predictor underneath, but suddenly it looks like maybe it's kind of trying to solve math problems. And if I say this thing about pretend you're a songwriter and write the lyrics for this song for this AI scientist who visits Rice to give a talk, well, now this thing is maybe a lyricist. So I asked Bard this. This is what it wrote. I don't know. I'll be performing it out in the lobby later. No, I won't be. So I don't know if it's like an expert lyricist. It's kind of a weird song to write. But you know, the point is, predicting what's next turns out to be able to be turned into solving almost any problem. Why is that? Well, language can express such a wide range of things that predicting it well can do almost anything. All right, so because of attention and these models, we now have language models that can understand seemingly language, can generate really interesting language and what comes next. We can apply it to a lot of problems. That's really cool, but there's still a bunch of hard issues to deal with before we can actually build products out of these things. Now, I could have talked about many different issues, but I chose these three. You know, that these models they struggle with factuality. They make things up. They don't follow instructions very well sometimes, and they struggle with higher order reasoning. And so I want to talk about each one and kind of what people are doing to deal with those things. So let's start with this is probably the most famous problem LLMs have, right? I'm sure you all heard lots of things about how, you know, LLMs lie and make things up. Sometimes you'll hear this called the hallucination problem, the grounding problem. The problem is that, you know, LLMs, really all they're doing is they're predicting what words come next, right? But there's nothing that makes those words be true, right? Those words statistically and according to the attention mechanism look and feel like good words that could come next in the right order, so these models are very fluent. But in fact, like, they have no grounding in truth per se out of the box. You know, they're kind of like, you know, a little kid who just likes to talk. Like, they know how to talk, and you ask them any question and they'll just answer, right? But like, that doesn't mean they know the right answer. Now, it sounds really bad, and look, if you're a lawyer, people I'm sure have seen this famous thing, you know, you maybe shouldn't write your legal brief, you know, using an ungrounded LLM. That wouldn't be a great idea. But if you're a creative writer who's trying to write a movie script or a children's story, look, you don't necessarily want a thing that sticks to ground truth. That creativity can be a good thing. But in a lot of cases, it's not. Let's just look at a few more examples. And I said I'm a product guy. Here's one of my team's products. I actually really love it. It's called MakerSuite. It's just an easy way to play with Google's models and even begin to train them in simple ways. And so the screenshots I'm going to have next are all MakerSuite. So it looks like this. You can all go use it. So let's try this for start. So this thing, which is called a prompt there, it says write your prompt. The prompt's just the input to the model. So this is the text that's at the beginning, and we're asking the model, when I hit that purple run button, okay, predict what comes next. Okay. Well, Rice University was founded in 1912. That turns out to be true, I think. I hope it is. I looked it up. So great. So this time it kind of got it right. But now if I switch it to Paperclip University, you know, it's a little known thing. It turns out Paperclip is a lot more prestigious than Rice, right? I mean, it was founded earlier, right? And the model happily answers that. So let's try another one. Let me ask for some marketing help. You know, I really like it here at Rice, so I want to write a marketing brochure, but I think the brochure should really talk about, you know, this great major that I know you guys offer. I won't read it to you, but, you know, just as you can see how it starts out, Rice University, the comprehensive basket weaving education. It goes on to talk about the amazing program, the great faculty, the amazing. Is anyone here from the basket weaving department today? So this kind of shows like what's hard about this, right? Like this thing I mean, at least to me, it sounds very good. Like it sounds credible and all that, and yet it's just not true that there's basket weaving. Now you might say, well, look, Paperclip University, this basket weaving thing, like with your prompt, you're kind of misleading the model, or you're kind of asking it, you're leading the witness here or something. But even for a simple factual question like this, so have any profs from Rice ever won the Knuth Prize? If so, who? Simple factual question. And the model happily answers, yes, in fact, it's Donald Knuth himself. Was a professor here at Rice, and I guess awarded himself his own prize, you know, a while back. Now, obviously, again, sounds confident, but it's not true. So how are people dealing with this? Well, I want you to think about, since we have educators here, and teaching is the new programming. So how would you deal with a student who had this problem of kind of not really supporting their facts? Well, presumably you would say, look, before you spit out your answer, you need to go get information from trusted sources, right? Don't just say the first thing that comes to your head. Go like look it up and get information. And that's a pattern that is emerging really strongly in AI. Now, people call it retrieval augmented generation. The model is generating, and we're going to augment what it generates with retrieval. And so it works kind of like this diagram here, where up there at the top, I take my ground truth, my source documents, my information. I put them into, I'll call it a smart index. It's also kind of an LLM thing usually. And then when I ask my question, before I have the answer LLM answer, I go find some relevant information from that smart index, and I put it into the prompt, the input, and say to the LLM, like, answer this way. So, for example, if I got this question about the Knuth Prize from Rice, well, maybe my source is like the Rice website. Maybe I'll use that as my source, put it in my index, and then I'll give my LLM some relevant passages. So I tried this. I was the smart index in this case, or the index on the website was. So I found these 3 paragraphs that are potentially relevant. And you don't need to read them, but they're all about computer science professors winning prestigious prizes here at Rice. And then I put that into MakerSuite. And the question at the top, you can see I preface my thing by saying, hey, please answer the question below using only this following information and answer with a complete sentence. And then I pasted in my 3 paragraphs and asked my question, and lo and behold, it turns out that Moshe Vardi actually is from Rice University and actually won the Donald Knuth Prize. Now, you might say, well, yeah, I mean, come on, it's right there in like the second paragraph, like you gave it the answer. And yeah, that's kind of the point of this, is that by helping the LLM to have some choices and some information that's relevant, usually it can then answer. Now, this is a simple question, but it could have been something more complicated. You can imagine I could put, for example, retrieve a bunch of information about events in the Civil War, and then I could say, hey, LLM, please make a timeline for me of the most important events and a summary of each one, right? And then the LLM presumably could do that. So this can be more complicated than a simple question. Now, with some more complex systems, like Google's Bard system, the model actually can draw information from a bunch of different sources. And so what people are doing is actually teaching a first LLM to figure out, given a question, what are those information sources? Is it about flights, hotels, maps? And then I could go get information on the fly. So just to show you a simple example, this is Bard. This isn't MakerSuite. I asked Bard what hotels are available near Rice University October 31st. And you can see kind of the first LLM says, oh, that thing is a Google Hotels question. And actually the parameters of it are that this certain date, and it made up that it's 2 people because I didn't say. And then I actually got back a list of real hotels and real prices, as opposed to if that hotels piece wasn't there, the LLM would happily invent hotels and tell me their availability. All right, so you can talk a lot more about hallucination and factuality, but those are a couple ways. But the basic idea is, hey, pull in information from trusted sources, and LLMs can answer better. So let's go to the second problem. I'll call it the instruction following problem. Look, again, LLMs, they're just guessing what words come next, but a lot of times what we want is something a little more specific. We want the words we're giving the LLM are instructions, and we want the LLM to actually follow those instructions to the T in answering. And these days, because these things are powerful, people are writing actually very complex instructions. If this, in this case, with this input, do this, and want the LLMs to follow that. But the problem is that, just like maybe some of your students or kids, I don't know, they don't do, here's an example. So I asked the LLM, hey, write a 3-sentence description of Tom Brady and use the word baseball. And again, just like my kids, it just completely blew me off, right? I mean, it's about Tom Brady, but there's no baseball in there. It's like, hey, why don't you answer me? So again, with our students, what would we do with this? Well, teaching is the new programming. And I think what we end up doing to teach people how to follow instructions is, first of all, give examples, right? Hey, here's what a good answer looks like. And so you give your student a few examples, then you hope that they're going to figure it out. The other thing you can do is give your student feedback, right? You ask them to do some, and then you say, yeah, this is good, but no, this isn't, you didn't follow the steps that I asked you to follow for this one. And they hopefully learn from that. So I go back to my bottom trying to build that uses a word in a description. Here's a bunch of examples. You don't have to read them, but what the examples say is there's a topic to describe, I give it a word to use, and then the description I give is an example of what I want it to do. And obviously, everyone is a description of the topic that uses the word that I asked for. And the way we use this is a process called tuning. Tuning is basically teaching the model to do a new thing. And what this diagram is showing is, look, we build these models from a giant web-scale database, we talked about that, to form kind of our basic model. But then there's a way called fine-tuning where we can basically layer in even a very small number of examples like the ones that I showed there. Really, it's like 20 examples, and get an LLM out that's actually fine-tuned or trained to do that specific task. Now in MakerSuite, if you try it, it's one thing I'm proud of, super simple to do. You literally can just upload your spreadsheet, hit train, and you get out a trained model in about 3 minutes. Whoops, that slide's old one. And now, when I say, Tom Brady used the word baseball, the LLM figures out a way to use that word. He's also a fan of baseball. Now, I don't know if he is or not, but at least it uses the word. And it turns out if you play with this, even trained on these 20 examples, this model is actually pretty good at this. I didn't do a scientific measurement, but I tried lots of hard ones. I really like this third one down. Right? The topic is rice and the word is anthropomorphic. I did not know what was going to come out of these, by the way. And you can see the second sentence says the university's mascot is an anthropomorphic owl. Is it? I don't know, is it? Yeah. Some say yeah, okay. So pretty, so these models get pretty creative, but now it's really trying hard to follow my instructions because I've taught it what to do. Now, I'll just mention this really quickly, that a second way that people are training these models to follow instructions is kind of by grading their work. And we can call it, the name for it is, people call it reinforcement learning from human feedback. It's really a key way that systems like ChatGPT and lots of others actually work well. With your students, you can grade one assignment at a time, and you hope that they learn. With these models, what people do is actually come up with thousands or even millions of inputs that they want the model to perform well on, send it through the model, and then have humans or maybe other models score the results, and then learn a new model that is actually able to predict the grades. And then that gets mixed back into the original model. So, basically able to kind of take those human grades at huge scale, and this makes these models perform dramatically better. All right, so we've made our LLMs more factual by teaching them to use trusted information and to follow instructions with examples and taking feedback. The third problem is I'll call the reasoning problem. LLMs, they're word predictors. They spit out words, but some things that you want to do, like, it's not the right thing to just spit out words. Like, you got to think about what you're doing. So if you gave your student this problem, please write an academic research paper about this thing. Like, what you don't want is for that student to say, okay, here goes, blah, 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 blah. Start writing down the paper. That'd be really weird. It's like, well, no, you didn't do the research yet. Like, you got to come up with a plan. You got to come up with a theory of what's better. You got to, develop that. Then you got to do experiments. Come back in a year, right? And you can write the paper then, right? But by the way, if you click run on this, the LM will very happily spit out a completely fake-looking thing that says that claims it invented a new way to, to do whatever it is the paper. Now, obviously, believe me, LMs are not going to replace your grad students. They're nowhere near doing this thing. But even simple math problems are like this, right? Here if I gave the system an example of a math problem to do, a word problem, then I gave it a second one, and it happily generates an answer that has the form of money, because it's a money problem, but it's completely wrong. And if you start hitting run over and over, it'll just generate a new number every time. It's just happy to answer again, like a little kid who blurts out the answer. All right, so what do we do about this? Well, again, teaching is the new programming. And so why can't we teach our LLM, again, what I think we would teach a student in that math class, which is, look, you got to break down the problem into its steps, and you got to do it step by step and think it through, right? So here's another version of the problem. This, by now in the AI world, is really old, because I think this is like a year ago, this thing. So some of you, I'm sure, have seen it. This just blew my mind when I saw this thing. So here's an example, same kind of thing as mine. Here's a question, the next one, it just guesses at the answer. But it turns out if you just add a little bit to your input, this part that's in blue, and you just add basically the steps. So in your example that you show, you add the steps. Roger started with 5 balls. 2 cans of 3 is 6. 5 plus 6 is 11, so the answer is 11. So you're just showing it Here's how you think through the problem. Just one example. All of a sudden, the LLM can spit out that same kind of answer for a new problem. It's really mind-boggling, actually. This technology can actually be taught even to do thinking and chain of thought with just a simple example. By the way, not just that one, it can now solve many examples, having just seen that one. And you can imagine that people have now gone nuts on this over the last year and have been many chains of reasoning and all kinds of things. This is one I just happened to come across like a couple days ago, where someone said, oh, well, I want my LLM to answer math questions in base 9. And it turned, of course, it can't do it at first, but then they just added this simple, what they called a rule library of like, well, here's the sums of single digits in base 9, and all of a sudden, like the LLM can answer base 9 problems. So pretty amazing thing, especially when you consider that all the LLM really is predicting what comes next, but sometimes you can predict the right answer even to a math problem. All right, now we all know that sometimes problems are harder than just thinking through steps and then executing them. And in particular, sometimes you have to go out and actually get information, bring it in step by step, and reason through a problem. And people are working on many architectures like that to help LLMs think through problems piece by piece that are more complicated. One technique which we use a lot at Google in my team is called React. It just means first kind of reason about what's the next step of the problem, and actually we ask the LLM to explicitly write out what you think the next step is, and then to write out what action would help you do that next step, and then go execute it. So like if I'm trying to make progress and I need to figure out more about X and Y, and maybe the action I can do is do action Z, and then I go do action Z, and then I actually run the LLM again in a loop, but I put the results of action Z in there. And the LLM continues to think through what's the next step in the problem. So here's a very contrived, admittedly, example. Author David Chernoff is associated with the US Navy Admiral, served the ambassador to the UK under which president. Now, it's contrived because you can see that obviously what would you do? If I asked you to do this, first you'd say, like, I'm not doing that. But after you got over that, you would start by thinking, well, I better look up this David guy and see if I can see the admiral in there. And then I'll look up the admiral and see if I can find the president. If I can do that, then I'm done. And this React method actually does essentially that. This is an eye chart, but each column really represents first looking up first generating the look for David, then we get the information about the admiral, and then we get that the president was Bill Clinton. So these kinds of techniques are allowing LLMs to run in a loop, and thus basically, instead of having to do everything in one shot, actually do problems that exist kind of over time. And this example is silly, but people are even using this for stuff like robotics and planning robot motion that's complicated, and all sorts of other step-by-step kind of planning problems. A lot of variations. All right, so let's pop back up here. Look, language is hard because meaning changes with context. In very subtle ways and with long-range dependencies. Attention is the mechanism that allows language models to understand that context and meaning, and therefore to predict what comes next. And predicting what comes next turned out to apply to all kinds of problems that we all have. The three issues that come up, well, the models lie, but hey, we're teaching them how to go get the right information. The models don't follow instructions, but you can kind of make them follow instructions if you show them examples and give them feedback. And they can even exhibit beginnings of higher order reasoning on more complex problems by teaching them how to break the problem down and do it piece by piece. All right, so I want to close with this, which is, I said I'm a product guy. I can't resist showing you one other product. This one is really cool. It's called Notebook LM, and the idea of it is that in this product, you actually upload a set of sources you're trying to learn about and trying to understand and trying to recombine. And then you can ask questions and do a lot of creative things with those sources to actually create something new. The reason I thought it might be interesting for all of you to see is we're actually piloting this at, I think, 5 different universities this fall in different courses with professors and students as a way to help students absorb information and begin to learn. And I think with all the, obviously there's all the very understandable narrative of like, well, aren't students just going to use AI to like cheat and write their essay for them? So this is, we're trying to kind of get at how can the AI really be more of a thought partner for you. So let me just play this short video to close up here.
In this demo of Notebook LM, Imagine I'm a student trying to review information for a project in an American history class on the Cold War. I start by uploading some of the class reading as sources in my notebook for the class. Immediately, Notebook opens up one of those sources. It's a chapter from my textbook, and the AI creates a guide for the content of the chapter with a summary and key topics so I can get my bearings. You can see all my sources lined up on the left here, and you can see Notebook LM also gives me a list of suggested questions based on the class material. But I'm going to start with a question of my own about foreign policy. The AI gives me a helpful answer grounded in my sources. So let's say I want to capture that information to review it later. I can pin this response as a note with one click. And this is important. I can always see the citations from the original source that the model used to generate its answer. And with one click, I can jump back to see the quote in its original context. With Notebook LM, you always know where information comes from, so you can fact check or acknowledge an author. Now let's say I want to read a slide deck that my teacher has prepared. I can easily switch over to that source and start reading. And here I come across a passage that might be important to review. So I select that text, and instantly Notebook LM gives me a series of options, like help me understand. But in this case, I want to capture the core ideas in the passage. So I choose Summarize to Note, and it's added to my notebook. Now let's say I've collected a bunch of notes and quotations and interesting responses from the AI. I want to organize all that information into some kind of structured format. I can select all my notes, and as you can see, I can now transform that specific collection in all kinds of ways. I could create a study guide, for instance. But in this case, I want to create an outline. And this outline's looking pretty good, but I want to make sure that I'm not missing anything. So I choose Suggest Related Ideas, and the Notebook LM AI analyzes both the content of the outline and the content of my sources to figure out what I'm missing. I add the suggested ideas to my outline and export to docs, and I'm ready to start working on the final version of my project.
All right. Pretty cool, right? No? Oh, I gotta find my cursor again, sorry. All right, so what have we seen? LLMs are transformative. They're amazing. Maybe they're going to be as impactful as the mobile phone. Attention is the mechanism that makes them work. And yeah, they struggle with making things up and not following instructions and not being able to reason. But using the kinds of ways we teach our students, we're starting to make progress on all those problems. You know, I just believe that together we're really at the start of kind of a new era where we can use language to actually create new capabilities for computers. And if you kind of think about it, instead of being limited to a tiny number of people who are programmers who can do that, maybe we're going to be in a world where a much larger group of people can actually create things and teach computers new capabilities. Teaching is the new programming. So what will you teach computers to do? Thanks very much.